Hello everyone, I'm Xinqi. Our paper is Learning Disentangled Representations with Latent Variation Predictability. Let me first introduce our motivation. We consider the image pairs generated by a generator with a different latent dimension in the latent codes. So these two image pairs are generated by two latent codes, but they only differ in a single dimension, and this dimension is represented by the varied dimension code. But actually you can see the rest of the codes are the same. So actually these two image pairs only differ in the aspects that controlled by the single dimension here. We can see this variation code not only correspond to a single image pair, but a bunch of image pairs, because the rest of the code can also vary. Like here we show 3 pairs, and then for every dimension of the, if we represent it as a varied dimension, they can also represent a bunch of image pairs that differ in that type of aspects. Then we require a model to do a reverse prediction, meaning we use the image pairs to predict which dimension is varied, which corresponded to the image pairs for each row. In this way, the image pairs can be seen as a data set with the varied dimension as the labels to be predicted. Then this prediction is supposed to be easy for disentangled representations. This is because the variation pattern shown in the data between image pairs is considered as consistent for each dimension for a disentangled representation. And for different varied dimensions, these variation patterns between each group of image pairs should be very distinguishable. And that makes this type of a reverse prediction easy. On the other hand, this prediction is hard for entangled representations because the varied pattern shown in image pairs are not very consistent compared to disentangled representations. So they may require more image pairs to train a good model to predict which dimension has been altered in the latent space. So that's why we consider it as hard. We name this type of prediction as latent variation prediction. And the easier this prediction is, the more disentangled a representation is. Now let me introduce you our proposed method. We decide to encourage a model to be more disentangled by forcing the model to have higher latent variation predictability, which is the prediction we mentioned earlier. To achieve this, we propose to maximize the mutual information between the index of each latent code that is varied and the corresponding image pairs generated by the variation code. Then this can force the model to generate image pairs that can preserve most of the variation information inside the images. And here, this is the varied latent code, and here are two variables to represent the image pairs. In our implementation, we actually maximize the lower bound of this mutual information to simplify the implementation. Here is the architecture we propose to train the model. It first starts with a general GAN, which takes a latent code as input, also some noise, and then is a generated image which passed to a discriminator to obtain the adversarial loss signal. And actually, we equip this GAN with another branch, which we sample not only one but two images, which is the image pair, but with two latent codes, but the latent codes only differ in a single dimension. The index is indexed as D, and here is the variation code. Then we take the two image pairs as input to a recognizer. The recognizer will output a prediction to the various dimension in the latent code. And we use the cross entropy loss for this to form our variation prediction loss. Then we introduce the our proposed disentanglement metric based on the variation predictability. As we have mentioned earlier, latent variation prediction is easy, which corresponds to the disentanglement. However, on the other hand, when this prediction is hard, that means the representation is entangled. Then we can use this as a proxy to evaluate the disentanglement quality of a generator. Specifically, we evaluate a generative model. To evaluate this, we sample multiple latent codes that only differ in latent code pairs that only differ in a single dimension. Like here, for each latent variation, we can sample multiple code pairs, because the rest part and also the varied dimension itself can also be different for each sample, but only just to keep the code, the gap between the two pairs the same. Then we can also generate image pairs based on this sampled code. And then, as we mentioned earlier, these image pairs can be seen as the input to a input of a data set, and the varied dimension is seen as the labels. And this is a data set which can be used to train a model. Then we can train a simple ConvNet using this data set to train a classifier. Then this prediction, if this prediction is easy, we can classify this model as disentangled. And if it's hard, which means it's entangled. And this hard and easy can be evaluated using the performance of this prediction. Okay, that's the introduction of our model. And here I will introduce some results, quality results of our model. As we can see, our model can achieve a cleaner disentangled representation than the InfoGAN counterpart. To mention that these two models are using the same architecture. As we can see, the InfoGAN has a more entangled representation for azimuth and smile, and also for fringe and genders. Our model achieves a better disentangled representation. And also, our model can achieve more subtle variations that like the right and fringe control, and also like the forehead width control and the forehead height control, which haven't been shown in the earlier literature. So that's it. That's our paper. If you're interested in it, you can come to ask some questions and read our full paper. Thank you.